In the far future, the universe could become a lonely place, with only our local group of galaxies remaining visible. Understanding dark energy is one of modern science's greatest challenges, because it may hold the key to the universe's ultimate fate. Some black holes are surrounded by swirling disks of fire. Material falling toward a black hole doesn't plunge straight in. Instead, it forms an accretion disk, a swirling, flattened ring of gas and dust heated to millions of degrees by friction and gravity. These disks glow brilliantly in X-rays and other high-energy light, making them visible to telescopes, even though the black hole itself is invisible. In the most active galaxies, these disks can outshine the combined light of every star, earning them the name quasars. The inner edge of the disk spins close to the speed of light, and magnetic fields can channel some of the material into powerful jets that extend for thousands of light years. Accretion disks are extreme environments where matter is torn apart, heated, and transformed, the final stage before crossing the event horizon and vanishing forever. Stars can be torn apart by tidal forces. When a star strays too close to a black hole, the difference in gravitational pull between its near and far sides can rip it apart in a violent process called spaghettification. The star's material stretches into a long stream, with some flung into space and the rest spiraling toward the black hole, heating into a bright flare that can outshine the host galaxy for months. These tidal disruption events are rare, but they provide astronomers with valuable opportunities to study both black holes and the final moments of doomed stars. The physics behind them is the same as ocean tides on Earth, gravity pulling more strongly on one side than the other, but on an incomprehensibly more destructive scale. Astronomers have found a planet where it rains glass. Far from Earth, in the constellation Pegasus, lies a planet called HD 189,733b, a gas giant orbiting so close to its star that its skies are a deep, vivid blue. But this color isn't from oceans or clear air. It's from silicate particles high in the atmosphere, which condense into glass-like droplets. Supersonic winds whip these particles sideways at speeds of up to 7,000 kilometers per hour, meaning that on this world, it quite literally rains shards of glass, hurtling through the air in a deadly storm. It's a place where beauty and danger exist in the same moment, a sapphire world glinting in starlight, but one no spacecraft could survive. Some galaxies contain trillions of stars. While the Milky Way holds hundreds of billions of stars, some galaxies, such as giant ellipticals, are far more massive, containing trillions. These cosmic giants often form through multiple mergers over billions of years, growing larger with each collision. Their sheer size means they can dominate galaxy clusters, influencing the motion of smaller galaxies around them. At their centers often lie supermassive black holes, many times the mass of the Milky Ways. From a distance, these galaxies look smooth and featureless, but up close they are densely packed with ancient stars, each one a sun with its own history. They are vast stellar metropolises, reminders of how diverse and grand the architecture of the universe can be. Time may flow differently in other parts of the universe. Einstein's theory of relativity shows that time is not absolute. It can pass at different rates depending on gravity and motion. In regions with intense gravitational fields, like near black holes, time slows relative to areas with weaker gravity. Even velocity can change the passage of time. A spacecraft moving near the speed of light would experience time more slowly than observers at rest. This means that across the universe, now is not the same everywhere. The idea has strange implications. Two events happening at the same moment from one viewpoint may occur at different times from another. The cosmos, it seems, doesn't have a single clock, but countless local ones, each ticking to the rhythm of its own surroundings. there are clouds of alcohol in space. In the vast molecular cloud, Sagittarius B2, near the center of the Milky Way, astronomers have detected massive quantities of ethanol, the same type of alcohol found in drinks. This cloud spans hundreds of light years and contains enough alcohol to fill trillions of pints. Of course, it's mixed with other chemicals and is far from drinkable, but its presence shows that complex organic molecules can form naturally in space. Such molecules are created on dust grains and released into space by radiation or heat, offering clues about the chemistry that may lead to life. Sagittarius B2 also contains other intriguing compounds, making it one of the richest chemical treasure troves in our galaxy. Some stars are on collision courses with each other. Stars are not fixed in space, they move through the galaxy under the influence of gravity. In most cases, these paths never cross. But in dense star clusters or binary systems, close encounters can happen. Some stars are locked in orbits that will eventually bring them together, merging into a single, more massive star. These stellar collisions can create unusually bright stars known as blue stragglers, or trigger nova-like events as their outer layers interact. In rare cases, they may even collapse into black holes or neutron stars. Such collisions are relatively rare on human timescales, but inevitable over the galaxy's long history, reshaping star systems and creating new cosmic wonders. The Sun will one day become a white dwarf. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and swell into a red giant, engulfing Mercury and Venus, and possibly Earth. After shedding its outer layers into a glowing planetary nebula, the remaining core will collapse into a white dwarf, an Earth-sized remnant composed mostly of carbon and oxygen. This dense object will slowly cool over trillions of years, fading into a black dwarf, cold and dark. White dwarfs are common endpoints for stars like our Sun, and studying them gives astronomers a glimpse of our solar system's far future. Supermassive black holes can control entire galaxies. Though confined to the centers of galaxies, supermassive black holes can influence regions hundreds of thousands of light years away. When actively feeding, they release jets and winds that can heat surrounding gas, preventing it from collapsing into new stars. In other cases, they can compress gas clouds, triggering bursts of star formation. This process, known as feedback, shapes the growth and evolution of galaxies over billions of years. Without the regulating influence of their central black holes, many galaxies might look very different, either choked with newborn stars or depleted entirely of star-forming material. The vacuum of space can boil your blood. In the absence of atmospheric pressure, liquids boil at much lower temperatures. This means that in the vacuum of space, unprotected human skin and fluids would experience ebulism, where water in the blood and tissues starts to vaporize. It wouldn't be a dramatic explosion. Your skin is strong enough to keep your body intact, but swelling, dizziness, and loss of consciousness would occur within seconds due to lack of oxygen. Astronauts rely on pressurized suits to maintain normal conditions, preventing these dangerous effects. Space's vacuum is not inherently cold or hot. It simply doesn't conduct heat well, so you'd lose warmth through radiation rather than touch. While we'll never be exposed like this outside fiction or accident, the reality underscores how hostile the cosmos can be and how vital the thin shield of our atmosphere is to our survival. Some stars pulse like beating hearts. Certain stars expand and contract rhythmically, growing brighter and dimmer in a steady pattern. Known as pulsating variable stars, these changes are caused by cycles of heating and cooling in the star's outer layers. Cepheids variables, for example, are so regular that astronomers use them as standard candles to measure distances across the universe. The periods of their pulses correspond directly to their intrinsic brightness, making them invaluable cosmic yardsticks. Other types, like RR Lyrae stars, pulsate more quickly, often in just hours. Watching their light curves is like tracking a heartbeat, revealing not only their size and structure, but also clues about the history and age of the galaxies they inhabit. Some stars burn so hot, they could vaporize you instantly. The hottest stars in the universe burn with temperatures exceeding 50,000 degrees Celsius at their surfaces and millions of degrees in their cores. They shine in a searing blue-white light, pouring out intense ultraviolet radiation that would strip away an atmosphere in moments. If Earth orbited one of these stellar furnaces, our oceans would boil away almost instantly. Such stars live fast and die young, burning through their fuel in just a few million years, a blink of an eye in cosmic terms. Their ferocity shapes galaxies, triggering the birth of new stars and carving vast bubbles in the interstellar medium. Yet from our safe distance, they are simply brilliant points in the night sky, their violence softened by the trillions of kilometers between us. Looking at them is to see both beauty and destruction in a single glance, the dual nature of the cosmos itself. There may be hidden oceans larger than Earth's beneath icy moons. Beneath the frozen crusts of moons like Europa, Enceladus, and Ganymede, scientists believe there may be vast oceans, some holding more water than all of Earth's seas combined. These alien oceans are kept liquid by tidal heating, where the moon's interior flexes under the gravitational pull of its planet, generating warmth. In darkness far from any sunlight, life might still thrive, drawing energy from hydrothermal vents on the ocean floor. Plumes of water vapor have even been detected erupting from Europa and Enceladus, hinting that their oceans might one day be sampled without drilling through kilometers of ice. These worlds are tantalizing because they suggest life could exist in places we once thought impossible. When we look up at Jupiter or Saturn, we're not just seeing distant planets. We may be looking at entire ecosystems hidden in the cold, waiting for the first human-built probe to dive beneath their shells. There are moons covered in ice geysers. Saturn's moon Enceladus and Neptune's moon Triton both exhibit plumes of material erupting from beneath their icy crusts. On Enceladus, these geysers spray water vapor, ice particles, and organic molecules hundreds of kilometers into space, feeding Saturn's faint earring. Beneath the surface lies a global ocean kept liquid by tidal heating from Saturn's gravity. On Triton, nitrogen geysers vent material high into its thin atmosphere, driven by seasonal warming of its frozen surface. These icy plumes are more than spectacular sights. They offer a way to sample hidden oceans without drilling, and they hint that even distant frozen worlds can be active and possibly habitable beneath their shells. Space has no true up or down. In the microgravity of space, directions like up and down lose their meaning. Astronauts aboard the International Space Station can work in any orientation, flipping upside down without feeling inverted. Instead of gravity determining direction, astronauts orient themselves using the structure of the spacecraft, often choosing a floor and ceiling for convenience. In deep space, the concept becomes even more abstract. There is no universal reference for up or down, only relative positions between objects. This lack of fixed orientation is one reason space navigation relies on star maps, gyroscopes, and sensors rather than intuition. The idea can be disorienting, but it's a reminder that our sense of direction is shaped entirely by life on Earth. A black hole's gravity can slow time to a crawl. Near the event horizon of a black hole, gravity is so strong that it warps space-time dramatically. To a distant observer, a clock near the horizon appears to tick more and more slowly, approaching a complete standstill as it reaches the edge. This is gravitational time dilation at its extreme. From the perspective of the person falling in, time passes normally. but the outside universe appears to speed up. In theory, one could witness millions of years of cosmic evolution in moments before crossing the horizon. This strange reality has been confirmed in less extreme cases by experiments on Earth and satellites in orbit, proving that time truly is flexible in the presence of intense gravity. There are rivers of stars in the Milky Way. Our galaxy is crisscrossed by vast stellar streams, elongated trails of stars that were once smaller galaxies or star clusters pulled apart by the Milky Way's gravity. These rivers can stretch for tens of thousands of light years, wrapping around the galaxy in graceful arcs. Studying them reveals clues about the Milky Way's past mergers and the distribution of dark matter shaping its gravitational field. The Sagittarius stream, for example, is the remnant of a dwarf galaxy currently being absorbed. These rivers are cosmic fossils, preserving the memory of events that unfolded over billions of years. Planets can orbit in opposite directions around the same star. In some rare multiplanet systems, one planet orbits in the same direction as the star's rotation, while another moves in the opposite direction. This retrograde motion is often the result of gravitational disruptions, such as a close encounter with another planet or a passing star. These chaotic events can flip a planet's orbit, creating systems that defy our expectations of orderly formation. Such configurations challenge current models of planetary dynamics and hint at the violent histories that shape solar systems. Some galaxies are shaped like perfect rings. Ring galaxies form when a smaller galaxy passes through the center of a larger one, triggering waves of star formation that spread outward in a circular pattern. The result is a glowing ring of young blue stars surrounding a relatively empty core. Some rings are nearly flawless, looking like cosmic ripples frozen in time. The Cartwheel Galaxy is one of the most famous examples, its structure a product of a galactic collision millions of years ago. These unusual shapes are fleeting on cosmic timescales, lasting only until the stars disperse and the galaxy settles into a more typical form. There are stars that change color as they age. A star's color depends on its surface temperature, which changes over its lifetime. Young, massive stars burn hot and blue, while smaller, cooler stars glow red. As stars exhaust their fuel, they can swell into red giants, then shed their outer layers to reveal hot, blue-white cores. Some even pass through multiple color phases in relatively short periods. Observing a star's color and brightness gives astronomers insight into its mass, age, and chemical composition. In a way, a star's hue is a visible signature of its life story. A neutron star's magnetic field can shred atoms. Magnetars, a rare type of neutron star, have magnetic fields trillions of times stronger than Earth's. Such intense magnetism can distort the shapes of atoms, stretching them into long, thin structures and disrupting normal chemical bonds. These fields can also trigger massive starquakes on the magnetar's surface, releasing bursts of gamma rays detectable across the galaxy. The power of a magnetar's field is difficult to comprehend. If one were as close as the Moon, it could erase the data on every magnetic stripe and hard drive on Earth. They are among the most extreme and dangerous objects in the universe. The Sun's light takes 8 minutes to reach Earth. The photons that leave the Sun's surface travel at the speed of light, about 300,000 kilometers per second, reaching Earth in roughly 8 minutes and 20 seconds. But their journey actually begins much earlier, deep in the Sun's core, where nuclear fusion produces energy. There, photons bounce from particle to particle in a dense plasma, taking thousands, even millions of years to reach the surface. Only then do they stream freely into space. This delay means the sunlight that warms your face today began its journey long before humans existed. The 8-minute travel time also means we see the Sun as it was in the recent past. not exactly as it is now. In cosmic terms, this is nearly instantaneous, but it's still a reminder that even nearby light carries a whisper of history with it. Some planets orbit so close to their stars they glow red hot. Exoplanets, known as hot Jupiters, orbit their stars at blistering proximity, sometimes closer than Mercury is to our Sun. Their atmospheres can reach temperatures of over 2,000 degrees Celsius, hot enough to vaporize metals. Some are tidally locked, with one side in perpetual daylight and the other in endless night, creating extreme temperature differences. On the day side, the heat can be so intense that clouds of vaporized rock or metal form. These worlds likely migrated inward after forming farther out, pulled closer by gravitational interactions. Observing them gives astronomers clues about how planetary systems evolve, and it challenges our understanding of what kinds of planets can survive in such hostile conditions. There are places in space where gravity cancels out. In multi-body systems like the Earth and Moon or Earth and Sun, there are points where the gravitational pulls of the two objects balance perfectly. Known as Lagrange points, these regions allow a spacecraft to remain in a stable position relative to both bodies, with minimal fuel use. Some Lagrange points are home to swarms of natural objects, like the Trojan asteroids that share Jupiter's orbit. Others are prime spots for space observatories, such as the James Webb Space Telescope at Sun-Earth L2, where it has a clear, stable view of deep space. These balancing points are like the calm eddies in a vast gravitational ocean, where the push and pull of massive bodies cancel out. The universe was once smaller than an atom. According to the Big Bang theory, the universe began as an incredibly hot, dense state, smaller than a single atom, about 13.8 billion years ago. In a fraction of a second, it underwent rapid inflation, expanding faster than the speed of light. Space itself stretched, carrying matter and energy outward in all directions. Over time, the universe cooled, allowing particles to form, then atoms, then stars and galaxies. Though we often imagine the Big Bang as an explosion in space, it was actually the expansion of space itself, everywhere at once. The idea that everything we see today, billions of galaxies, once fit into a space smaller than a grain of dust, is one of the most mind-bending concepts in science. Stars can swap material with their neighbors. In binary star systems, the two stars can orbit so closely that one's outer layers spill over onto the other. This process, called mass transfer, can dramatically alter both stars' evolution. A star losing mass may shrink or even be stripped down to its core, while its companion grows more massive and luminous. In extreme cases, this interaction can trigger nova, sudden outbursts of brightness caused by accumulated material igniting on the surface of a white dwarf. These exchanges show that stars are not always solitary, stable objects. They can have relationships as dynamic and transformative as anything on Earth. Some galaxies are made almost entirely of dark matter. Astronomers have discovered galaxies whose visible stars and gas make up only a tiny fraction of their total mass. The rest appears to be dark matter, the invisible substance that exerts gravity but doesn't emit light. These dark galaxies are faint and difficult to detect, often revealed only by the way their gravity bends light from background objects or influences nearby galaxies. Studying them could reveal clues about how dark matter interacts with normal matter and why some galaxies fail to form many stars. They are ghostly reminders that most of the universe's mass is hidden from direct view. You can see the International Space Station with the naked eye. The International Space Station, orbiting about 400 kilometers above Earth, is the largest human-made object in space. When sunlight catches its solar panels just right, it appears as a bright, fast-moving point crossing the night sky. No telescope is needed, just timing. The station completes an orbit roughly every 90 minutes, traveling at over 27,000 kilometers per hour. From inside, astronauts see 16 sunrises and sunsets each day. Its visibility from Earth makes it a rare and inspiring example of space exploration you can witness with your own eyes. A moving star that's home to humans as it circles our planet. Black holes can merge into even larger black holes. When two black holes spiral toward each other, they lose energy in the form of gravitational waves, ripples in space-time predicted by Einstein and first detected in 2015. As they draw closer, their orbits speed up until they merge in a fraction of a second, forming a single, more massive black hole. The collision releases an enormous amount of energy, not as light, but as gravitational waves that travel across the cosmos. These events allow astronomers to study black holes directly, providing insights into their masses, spins, and how often they form. Mergers are among the most powerful events in the universe, reshaping space-time itself. There are giant clouds of gas larger than galaxies. In deep space, astronomers have observed enormous clouds of hydrogen gas stretching over 1 million light-years, bigger than entire galaxies. These colossal structures can serve as the raw material for future generations of stars and planets, or as the leftover debris from galactic collisions. Some are illuminated by nearby quasars, making them visible across billions of light-years, while others remain dark and hidden. Their sheer scale is hard to imagine. A single one could envelop the Milky Way and still extend far beyond. The speed of light is the ultimate cosmic speed limit. In the vacuum of space, nothing can travel faster than light, about 1.08 billion kilometers per hour. This limit is built into the laws of physics, affecting everything from the way we communicate across space to how galaxies evolve. Even gravitational waves travel at this same speed. For spacecraft, this means interstellar journeys will always require significant time. Even the nearest star beyond the Sun, Proxima Centauri, is over 4 years away at light speed. The speed of light is not just a number, it's a fundamental part of the structure of space-time, shaping what is possible in our universe. Some planets have rings more magnificent than Saturn's. Saturn's rings are dazzling, but they're not the largest or most complex in the universe. Astronomers have found exoplanets with ring systems hundreds of times larger, so vast they would dominate the night sky if seen from a nearby moon. One such world, J1407b, appears to have over 30 separate rings, stretching millions of kilometers in diameter. These rings may be made of ice, dust, and rock, and could one day form moons as material clumps together. The sheer scale of these structures challenges our sense of planetary beauty and makes Saturn's rings, magnificent as they are, seem modest by comparison. The Milky Way is moving through space at incredible speed. Our galaxy is not stationary. It's hurtling through the universe at about 2 million kilometers per hour, drawn toward a mysterious region known as the Great Attractor. This movement is the result of gravitational pulls from nearby galaxy clusters and the overall cosmic web. We don't feel this speed because everything around us, from the Sun to Earth's atmosphere, shares the same motion. Yet it means the night sky is never fixed. Over millions of years, the positions of constellations change, and our place in the universe is constantly shifting. There are planets with 2 or more suns. In some star systems, planets orbit not one sun but 2 or more, creating skies with double or triple sunrises and sunsets. These worlds are called circumbinary planets if they orbit both stars together, or multi-star planets if they move within a more complex gravitational dance. The varying positions of the suns could create extreme climates, with fluctuating heat and light patterns unlike anything on Earth. scenes reminiscent of science fiction worlds like Tatooine, are real, and studying them expands our understanding of how planetary systems form and survive in diverse environments. The universe might contain an infinite number of parallel realities. One interpretation of cosmic inflation suggests that our observable universe is just one bubble in an endless multiverse. If space truly extends infinitely, then every possible arrangement of matter could occur somewhere, including other universes where stars, galaxies, and even versions of ourselves exist with slight or dramatic differences. This idea is speculative, but it's consistent with certain mathematical models. While we have no way to directly observe these other realities, the concept stretches our imaginations to the furthest edge of possibility, blurring the line between physics and philosophy. Some stars die in collapses so violent they twist space-time. When a massive star collapses into a neutron star or black hole, the process can send powerful ripples through space-time known as gravitational waves. If the collapse is asymmetric, uneven in its distribution of mass, it can twist and distort space in ways we can detect from Earth. These events are incredibly rare to catch in real time, but they allow astronomers to study the physics of extreme matter and the behavior of gravity under the most intense conditions. Each detection adds to our understanding of how stars live, die, and leave their mark on the universe. There are asteroids with their own mini-moons. Some asteroids are accompanied by tiny companion bodies, small rocks captured by the asteroid's gravity. These moonlets can orbit for millions of years, or be lost after a close planetary encounter. The binary asteroid Didymos and its moon Dimorphos became famous in 2022 when NASA DART spacecraft intentionally collided with Dimorphos to test asteroid deflection methods. Such systems reveal that even small bodies can have complex gravitational relationships, and studying them can help protect Earth from potential future impacts. The Big Bang created more than just matter. When the universe began, it didn't just produce matter, it also created antimatter, light, and the seeds of all fundamental forces. For reasons not fully understood, matter came to slightly outweigh antimatter, allowing a material universe to exist. The Big Bang also left behind a faint afterglow, the cosmic microwave background, which still fills space today. Within fractions of a second, the laws of physics as we know them emerged, setting the stage for everything from the formation of atoms to the birth of galaxies. The night sky contains light from long-dead stars. Many of the stars you see have already ended their lives, especially those far away. Their light began traveling toward us long before they burned out, meaning we see them as they were, not as they are now. In some cases, the light is thousands of years old for distant galaxies. It's billions of years old. Looking at the night sky is, in a very real sense, looking into the past, a cosmic history book written in light, where each point tells a story from a different chapter of the universe's life. Every atom in your body was forged in a star. The hydrogen in your body formed in the first minutes after the Big Bang, but all heavier elements, carbon, oxygen, calcium, iron, were forged inside stars through nuclear fusion. When those stars died, they scattered their enriched material into space, where it eventually formed new stars, planets, and life. This means you are literally made of star stuff, your atoms recycled from ancient suns that lived and died long before Earth existed. It's a connection that links us to the cosmos in the most literal way possible. Somewhere in the universe, a planet like Earth may be waiting. With billions of galaxies, each containing billions of stars, it's statistically likely that many planets with conditions similar to Earth exist. Some may have oceans, continents, and atmospheres capable of supporting life. While we have yet to find a true Earth twin, telescopes are constantly discovering potentially habitable worlds in distant star systems. One day, we may detect signs of life, or even visit such a planet. Until then, the idea that somewhere, far beyond our reach, another world might be home to life offers both mystery and hope. And so, our journey through the cosmos draws to a close. We've drifted among planets and moons, through the hearts of stars, and to the edges of the known universe. Each fact, each story, has been a small light in the vast darkness, a reminder that even in the quietest hours, the universe is alive with wonders beyond imagining. Perhaps some of these thoughts have stayed with you, or perhaps they've already slipped away as you floated further into rest. That's the beauty of a night spent among the stars. You don't need to hold on to every detail. The vastness will still be there tomorrow, waiting for you. If you happen to still be awake, you can go ahead and explore more of our space journeys. But if your eyes are heavy, you can simply let yourself drift, carried by the quiet hum of the universe. Sleep well, and good night.